Yeah. So in this model, basically I propose an AI model, and this is this is the most basic configuration of the model, and it consists of the state and a transition function acting on the state, right? But this is really the most simplest dynamical system, the configuration, right? And when you talk about reinforcement learning, you always use this kind of configuration, right? And for control theory, you have this A, which is the action, right?
So you are talking about the reinforcement learning, right?
Yeah, reinforcement learning. So I don't need to go into too much detail, right? You already know this formula, right? So yeah, so reinforcement learning is governed by this Bellman equation, and it says that the value, this is the value function. Are you guys familiar with this reinforcement learning?
No.
Okay. So 全坡学习, right? And
I learned some reinforcement learning, but it's based on Q-table. There are some other algorithm, not based on this Jacobi equation.
No, this one is like a fancy name, but basically it's just the Bellman equation. Most people know this, the Bellman equation. It's really at the center, at the heart of the reinforcement learning. So every reinforcement.
So in your system, reinforcement learning, which one is agent? Which one is
but
function?
It's just the AI and interacting with the environment, the environment, right? This is the 环境, right? 环境.
No, you can use English. Yeah, so
yeah,
that's fine. So we want to know in reinforcement learning environment, which one is agent, which one is reward function, which one yeah.
Okay. Yeah. Okay. So actually it's reinforcement learning. We have the state, the reward, right? The state and actions, right? And what's the other? The observations or something. Yeah, there are four things, but that defines
evaluation function.
The value. Yeah, the utility function. So this defines the reinforcement learning problem. And for the state, it's just the working memory. So I explained here, it is the working memory of the agent. So whatever defines the state of the system, for example, it can be the chessboard, right? If you play chess, then the working memory, the state is the chessboard in chess, right? But for AI, it can be a set of propositions, logic propositions that defines the current state. So you know, for example, I am hungry, and the fridge is empty, right? Fridge empty. Now, these two propositions, they define the current state of the logic agent. So I would be talking about a lot about logic-based AI, and they define the current state of the agent. Okay, and
so sorry for interruption. So you are, I think before before this presentation, I think you want to talk about a more general topic about general AI, right? So right now you are talking about the reinforcement learning. So what's the relationship between general AI and reinforcement learning?
Yeah. So yeah. Okay. So I would be, because I study this logic-based AI for a long time, and a lot of the things I will draw from this background. But maybe, but this is not many people know about this topic, logic-based AI. But it is required to understand the theory, and the reinforcement learning is the whole framework for is the top level framework for the AI. So we try to put all this under the framework of reinforcement learning.
So reinforcement learning is a framework for logic-based AI, you mean?
Yeah. So
okay.
So then the logic state, I mean, the state is described by some logic formulas, right? And so we need to understand it this way. That the state is actually some logical structure. And so maybe I explain very briefly this one. Let me clear the window. Okay. So logic-based AI, so it's called logic-based AI, and basically you have some you have the knowledge base, and I usually draw it like this. It's a set of logic rules. Now so for example, for all x all humans will die, right? Are mortal, right? Mortal x. You understand this formula, right? All humans are mortal.
Yeah.
So this is one logic rule, and so we use this logic rule to deduce. This is the symbol for logic implication. So from a set of formulas to another set of formulas. So this is gamma. So we use the set of logic rules to deduce things. For example, from here, we say that Socrates is a man, right? So therefore, Socrates is mortal. We prove this, right? It's mortal. So yeah. So now from here we use an implication, and this comes from this logic rule, and this KB contains millions of maybe more than many logic rules. Right. So this is the whole idea of logic-based AI, and now I propose that this logic rule is also similar to the structure of BERT or transformer. Is transformer, but so this is the newest thing, because transformer, of course, dominates the current AI scene. Everyone using this is the state of the art.
Okay.
Right. So that's the most important aspect of my theory, is that I'm trying to make a connection between the transformer and also this logic-based AI. Right. Okay. And I go back to this, and so you understand why I put all this under the reinforcement learning? Is it okay now? So
Go ahead. Go ahead. So
okay.
So
the state is a bunch of logic formulas, and so all this is put under reinforcement learning. So for example, if the state changes, so I have some logic formulas, and those formulas will trigger the reward, because for example, that there is a logic proposition, and it says the agent knows something that is the target. So I give the reward when I found that proposition. Can you understand this?
Yeah. Sorry for interruption. Let me ask you a question. So you wanted to introduce a general AI. So because machine learning is divided into different types of machine learning, like supervised and supervised and semi-supervised. So because your topic is about general AI, so you want to use unsupervised machine learning style or model to do your research, right? That's why you choose reinforcement learning is your framework, right? So this is okay. Got it. Okay, go ahead. Okay. So now I understand. Why you choose because at the beginning you jumped into the reinforcement learning. I was a little bit surprised, because you wanted to introduce the general AI. Okay, right now I understand. Okay, go ahead. Okay.
Yeah. So it's the reinforcement learning is actually the most general framework for an intelligent agent. Okay. So you just put it inside an environment, and it can learn how to get the maximum reward, and that's the most general thing. But and also in comparison to the transformer, now you already know that the transformer uses unsupervised learning. It's also called self-supervised learning, right? You heard of this? Self-supervised.
You can talk. You can talk about a little bit for us about self-supervised. supervised
yeah.
machine learning. Yeah.
Yeah. So let me move down to the part. This one is the transformer, and let me see. So yeah. So now I talk a bit about the transformer. What is so special about this? So I need the other diagram, but it's not here. Do you mind? I find the diagram for a transformer, but
Yeah,
maybe
sure.
But maybe I just search for in Google the transformer.
Actually, we talk about attention transformer before, but actually nobody give us exactly what attention means. That's
Okay.
yeah. If you can give us the brief introduction about attention. Yeah, that will be great. Yeah.
Yeah. Can you see this? I mean.
Yeah.
Okay. Not very clear, but it's okay, I guess. So yeah. So by self-supervised, it means I mean I need to find some place to write. So it's self-supervised, and it means also means auto-regressive model. Have you heard of auto-regression?
Auto-regression.
Yeah. Auto-regression means now you input a sequence, right? You input a sequence and you want it to predict the next token. That's auto-regression. That's auto-regression. So sometimes the token is masked and you want it to predict this one, right? Given the context, right?
So what's the output of auto-regression?
Auto-regression means that the input and the output is basically the same, but
same.
Except that sometimes it's masked. But this is you don't know this, right? So you need to use the context to predict this one. But basically the input and output is the same, and that's why so it's called auto. Auto-regression. Yeah. Regression, it just means predicting what's missing. Okay. So this is self-supervised learning, and it completely revolutionized the field of natural language understanding, because now you can build a language model without any data. I mean, the data is just using raw data. You don't need any annotation.
Right.
So this is very powerful, and it allows the machine to learn all the meanings of the natural language, and it's very important. So it's self-supervised learning. And
right now, one question: how can we use this model to make a prediction about the question mark?
Right. So I can explain a bit. So have you seen this diagram? Is the self-attention inside the transformer, right?
Okay, a lot of questions. Yes.
But
Sorry.
You have seen this, right?
Yeah, I saw that. Yeah. Right now, we can see it.
So this is basically the most important structure of the transformer. It's the self-attention, right? And self-attention. Now, I want you to understand two things about this. So it is based on, I mean, the structure is there's this equivariance. Have you heard of equivariance of the transformer? Have you heard of this idea?
No, sorry,
So,
no.
for example, the input is x1, x2, x3, right? Now,
Okay.
if I change the input from 1, 2, 3, now if I change it to let's say 2, 3, 1, I mean change the order
Yeah,
of the input.
yeah,
Then what happens in the output is originally is it y1, y2, and y3, right? But
yeah.
now, but if I change the input, then the output would be y2, y3, and y1. It changes the same way. You understand
Okay.
it?
Yeah,
So
yeah,
it's
okay.
called equivariance. So if the
Oh,
input
okay,
changes, the output also changes the same way, exactly the same way.
okay.
And so this is one very important feature of the transformer. It's called equivariance. And now, what does it mean? What is the meaning of? I mean, why is this important? It's
Yeah,
because we are in this way. This x1, x2, x3 is actually a set of elements. Because inside the set, for example, I have apple, bananas, and oranges, and it doesn't matter how the order I enumerate them. It's
okay,
the same set, right? 1, 1, 2, 3 is the same as 2, 3, 1. There's no difference, right? Inside the
okay.
set, and therefore it captures the structure of a set instead of a versus a sequence. Now, I mean, in a sequence, the order is important,
Oh, okay.
right? But in the set, the order is unimportant,
Oh, okay.
and therefore the equivariance means that all the inputs and the outputs are the set elements, and yeah. So
Okay.
that's mathematically why this is important. And so you remember that there is they used to use RNN, the recurrent neural network,
Yeah, yeah,
to
yeah.
process sequences.
Right, right,
And
right.
but now but this is slow, and the transformer is much faster because the sequence is now x1, x2, x3, all this is broken down, and it's processed at the same time in parallel,
Oh, okay.
right? And
Okay.
it's broken down into the set elements, and therefore that's why we need to tell which one is the. I mean, we need to give more information about the position of the elements, and therefore we have the positional encoding. Have you heard of this? Positional encoding.
Yes, yeah, sure. Using
Yeah.
sine, cosine, that kind of.
Yeah, right. So we need to additionally we need to give the positional information into all these elements, because if we don't give the positional, then they are just the same. I mean, they will be, the order will be they will all be the same. I mean, 1, 2, 3 is same as 2, 3, 1. You understand?
Yeah. Yeah. So one question, your input is 1, 2, 3. So your output could be 6 different combination, right? So 1, 2, 3 output. Oh yeah, yeah. Output could be 1, 2, 3. Could be 1, 132 could be
no. Actually, the output, if you 1, 2, 3, then the output is 1, 2, 3 also. It's the same order.
Oh, it's same order. So
Yes.
so input is 1, 2, 3. The output is 1, 2, 3. But it doesn't matter
Yes.
what kind of order, right? So order, okay.
Yeah. So for example, if my input is 1, 2, 3,
Yeah.
then the output is not. It's not the same number, but it's the y1, y2, y3. But it's the numbers are different, but the order is the same. So only if you change, now for example, I change this to 2 and this to 1. So this, right? This goes here, and this goes here, right?
Okay.
If we change these two, we can see that the output is will be changed the same way. So these two will be changed. This will be swapped. But this is still the 3 is still the same. You see why? Because of these matrix operations.
Matrix operation.
Yeah. So I will go through this. So this is the key value, and then right.
What's the key and the value? Oh, we don't know. I don't know.
Okay. But yeah, I will explain. This is very important.
Yeah. Please.
So this maybe this diagram. Now that this is the self-supervised learning. You see, right? I just explained this. The sequence, and so we use this to do the prediction, and but sorry, yeah, okay, this one. So key value, but I mean it takes some.
What's the input there? Yeah.
No, I mean it actually goes back to this this idea. Now, this idea. So now what we want to explain the attention mechanism, and it came from, and it originally came from this paper of neural Turing machine. Neural Turing machine. And so we need to go back to explain what is a Turing machine, and you have the memory tape, right? You remember this memory tape, and then you have a finite state machine, which is the part of the Turing machine. But now this one has been defined in computer science, but it's more simple. It's just a finite state machine, and the Turing's invention is that he used this machine. In addition, he gave it the memory tape, which gives it the memory ability. So the finite state machine does not have an internal memory, but only Turing gave it the memory tape to make it a universal computing machine, which means that anything that can be computable is computable by a Turing machine. But if the finite state machine is not a Turing complete machine, it is much weaker. So, for example, that there's a language. For example, ABAB ... Now, this language can be recognized by finite state machine, and also some similar languages. But for example, if you have AN, BN, this language cannot be, it's not okay. This cannot be recognized by finite state machine. You know why? Because, for example, it recognizes A, B, B. Now, you have to count the number of A's and the number of B's, and it has to match this A and B and has to be the same. But the finite state machine cannot remember how many A's it has seen. So this cannot be recognized by a finite state machine. But only if it has the memory tape, then it can record how many times I've seen the letter A and how many times I've seen the letter B. And therefore, I can recognize that this is recognizable by Turing machine. You understand why? Right. For example, the finite state machine, I go, if I see the letter A, I go to this state, and I see the letter B, I go to this way, this state, right?
Yeah.
These two states. And so it can recognize this one, right?
Yeah.
But it cannot recognize this one because it doesn't know how to count the number of A's, right?
Okay.
So for example, it can count another A, B. So it will be A, B, B is okay, but it cannot count arbitrary number of N. It cannot do this. So that's why.
Got it. Yeah, can you continue?
Yeah, okay. So this is a Turing machine, and it can compute any computable function. But now we want to use deep learning that's why neural Turing machine, right? We want this to be a neural network to process. So what is the requirement? Is that we want it to be a neural network that is differentiable, because we need to do this, the error over the weights, right? The differentiation.
Yeah.
It's a gradient descent. And so we need to make the memory. So we need to address the memory using neural networks. And that's why they introduced the memory matrix. So the matrix M, and we use the content to address the memory. Content address. So what does it mean? For example, in the old way, you have the memory, the first memory, the second memory, right? And use the index I to address the memory, right? Traditionally, you use the index I to address the memory, but this is not differentiable. If the index I change from 1 to 2, index the I from 1 to 2, then the memory changes abruptly. And so it's not differentiable, right? You understand this?
Sorry, can you repeat here? So why if I change it from 1 to 2, it's not
differentiable?
Yeah.
Because you cannot say dy over di is not possible, because I is just an integer.
Oh,
right?
okay.
This is not possible.
Okay.
Right.
Okay, yes.
Now, so they use the content address, which means content addressable memory. So it means, for example, I have an item X. X is something I look for. It is a vector, and I look for this item. For example, it may be represent apple, and I look for this one in the memory, and it finds me the the closest item inside the memory to X. X is the thing that I look for, right? So, so M is the memory matrix. It has M1, M2, M3. It is a matrix, but I look for the vector that is closest to X, and it's return something for me. So maybe, yeah.
So contents address is continuously, so that's why they can do the gradient.
So So now maybe I draw the memory matrix. Now this is the memory matrix, and this has something here, and then the key. But this is the key and the value, right? And now there is another key, another value, right? Many of these. And what I find is that I have a query. The query, okay, and is the X I just talked about is a query, and I try to find the similarity between the query and the key. Like I compare the Q and the K and find the closest match. And it, for example, if this is the closest match, then I return this value.
Yeah, how can you define different set of key value? How to make?
Actually, we do the inner product of the query and the key. Now this is the inner product. You know this notation, right? It is also the same as sometimes they write Q K dot B, right? The dot product of the two vectors, right?
Yeah, we know that. But my question is, how can you generate your key value? Yeah, we know you have a different key value. How by using what kind of algorithm or rules you generate a key value, or you create a key value? I'm not sure.
I guess it emerges in learning. It's learned. So it's basically it's learned. So for example, these are the tokens in the transformer. So that are tokens. You know this concept. The tokens actually are like word embeddings, right?
Yeah.
Embeddings, and these are vectors, and they are actually learned. So you start with something random vectors, but then gradually they will become the word embeddings.
Okay.
I mean the word embedding actually is originally provided by another algorithm. The word vector algorithm. This one word to word, right? So
yeah.
So you input the word, then it gives you a vector and becomes an embedding, and then it's used for the query. Yeah, it's used for the query.
So in this case, we know. Okay, we know we can convert a lot of words in huge dictionary into a lot of vector, right? So, but where's the key value? Can you give us one example, simple example?
Yeah. So, for example, for like I need some more space. Let me write maybe right here. So for example, translation. You have a Chinese. You have a maybe this one 学生, and then you need to translate it to student, right?
Okay. Yeah.
So the 学生 is the query, and then the student, the English word is in the value. So you look up something and then it will return the value would be the English translation. And
so
this,
in this case, 学生 is a key, students is value, right?
Yeah, I think so. But if it's just one step, but sometimes it's many steps, right? But
yeah, but
yeah.
you give us is a translation scenario, right? So if it's not a translation scenario, how can we define the key value? That's my question.
But it is this memory matrix is learned. All the content of this is learned. So initially it's just random numbers. All these are random numbers, right? But you input the 学生, and then well,
no, this is okay. 学生 student is okay. This is just a very special case, right? So about the translation scenario, we got it. We know this. Yeah, but in general, it's not a translation scenario. It's how can you define your key value? You said it's learned from memory, metric memory, but I didn't get it. How can
So the memory content is learned. So initially the memory is, of course, it's just random numbers. It doesn't mean anything, but gradually it's learned to have the meaningful the memory content. So all the keys and the values, they are matrices, and they need to be learned. Maybe I find another diagram, but this one finished. So I have another. Sorry. Maybe this one. So it's the matrix, and so now this one is the input X, and then this is the matrix for, usually they write it Q, so this is QX, and this is K, the QK and V. Sorry, that there's no X here. No, so these are three matrices, Q, K, and V. And if you multiply X by this matrix, you get QX, which is the query. And this is the key. So this entire thing is like table lookup. It just, for each input you look up the, you can get the query, and you also get the key and the value.
Can you give us example? The
here
X, what kind of X could be input?
Maybe this word 学生 is a vector, right? 学生 is a vector. Now we get the query, which is just another new vector, and the key and the value. These are all vectors, right? And then you can use this to look up the value. So
But you just you explained the Xuexian
yeah,
is input and
yeah.
the key
So
the student
yeah. So maybe not self-attention. Why is it called self-attention? Because there is some memory. Now, for example, I have a sentence. For example, I am student. Right.
yeah.
So this is the sentence, and
Okay.
and there is some memory inside this context. I mean, it's called self-attention because the memory is inside these matrices. I mean these matrices is a kind of memory that you can look up between these words. For example, I use this word as the query.
So
Right?
in this case, what's the input? In this case, I am student. What's the input? What's the output?
Input is the English. I am student. English.
Oh, okay.
And
Input
maybe
is I am student. Okay.
Yeah. So the Chinese is here, the output, right? And so I use the word am as the query, and I look up inside this matrix. Now the query, there will be a vector, but all these other words, they have the key and value, right? The other words, but this one is the query, but the other words.
So query is am, I am. Yeah.
And
What's the key and what value?
the key, yeah. I explain here. Now the key and the value is for the word student, and there is the key and value for the word I, right? So they all of these have the key and values. So you remember the key and the value is the memory, right? Is the memory, right? There is the key and the value. But for each of the other words, for example, for this word I, there's the key value. For the student, there's also the key value. And I use the query, the queue, to match this key, match the key. And if it's the closest, then I will return the value. You understand? So there is actually some memory between these words. And then I look them up and then I find the value for this word, for the word being queried. But you have to look at this vertically, like this. Yeah. So I have a query and then I will have an output. And the output is the lookup of the memory of the key values in other words. Can you?
So each word, like I and student,
right,
consists of two parts. One is keyword, one is value.
Yes. So,
but sorry here. Why, if you don't use Chinese, can you give us another scenario? So you use key value query to yeah, because general AI, right? So we can apply general AI to many fields, not just the translation, right? I'm curious about, without using translation, student, 学生 to student, then how can you use this system? Yeah.
Yeah, but you understand the translation example, right?
Yeah, translation is okay. Yeah.
Okay. So, for example, I use the logic example. For example, human. If human X, then the mortal, right?
Yeah.
And there is an X here, and so, for example, now if you want to apply this rule, then you have to match human to mortal, and then X to X, right?
Okay,
and
go ahead.
This is also the similar to when we say a student match to 学生, it
Oh,
is
okay.
also similar. Yeah, and sometimes
So you first design one logic or rule, right? Rule.
Yeah.
Then you define the key value, right? So
yeah.
somehow I got it. Somehow, not
Yeah,
very clear, but somehow, yeah. Go ahead. Go
Yeah.
ahead. Yeah.
So yeah, it's kind of difficult to, but you just understand it like some kind of memory lookup. The whole self-attention is a memory lookup process.
Okay.
So let's go back to that slide.
Okay.
Let me see. So here, so it looks up some data, and maybe this. So maybe this diagram. So you have some words or input. These are the inputs, and this is the self-attention between all these elements. And every time you do this, you actually look up something. So it generates some output, and this is similar to having a logic rule.
Okay.
Sometimes I need the diagram so better to explain, but I'm not sure if I have those diagrams. Okay, this one, yeah. So this is from another paper, and let me see. So this is also self-attention. It's just similar, but it's from another paper, and they what they call the transformer circuits. Transformer circuits. But why they call this the circuit is because when you have self-attention, it's like selecting some items to give the output. So there are many tokens here, right? These are the tokens. All these tokens, right? But you see only this one. This is two paths. The paths, right? So these are only two paths that are selected, but the other paths has no function, right? These are not doing anything.
Okay.
And you know why this is like this? A bit. This is because the query. This one is the query, and it matches the key. The key is matched. This one, the query and the key matches, and also this maybe actually this, I think is this query also match this key. This is another key, and only if they match, then we have the values. We have this value, maybe v1, right, and this value v4, and they are added together. So this result is v1 plus v4. This is the result. It's added together.
Because
so
they have a same key?
Yeah, because they maybe not the same, but it's closest to the query.
Oh, okay.
They are both close, and that's why this is called attention, because the query is closest to the key, and they get attention. They get attended.
Okay, so it doesn't matter that these two keys they are same or not. The output is always v1 plus v4. You mean?
Let me think. So the query, I guess, it would be the same. I mean, the query. So the key would be both. They are both nearly the same. They have to be similar to Q. They are both similar to Q. Yeah. So in this case, they are this key K4 and K1 is that they're both similar to Q. Yeah. So because Q is similar to K1, therefore V1 is selected. And by the same reason, because Q is similar to K4, so V4 is selected. And then we have the sum of the values. So we can go back to this slide. Maybe sorry. Which one? Yeah, this one. So no, they have the key value, right? But this one is the query. Sorry. This one is the query for now, for this step. This is the query. You see why the input, it goes all this way to the query, right? And then this query is matched with the key value of this one, this attention. And then another attention is for this pair of key values. And then this attention. Can you see this? Right?
Yeah, yeah.
This is one query, and the query has so this query is X3.
So for one specified query, the group of key value, the number of group of key value are not same, right?
Yeah.
Because for example, the query one, there's a key one, value one, key two, value two, key three, value three, key 12, value 12. But for query two, there are only key one, value one, and key 24 and value 24, right? So how can we find the relationship between query and the number, a set of key value, a group of key value.
So, for example, for this step, we are looking at one step, and in this step, the query is X3 for this step. So the query, this input X3, it goes to here, to the query. And this query, it asks the question, are they the dot product? And it asks for this pair of key values, and then also this one, and also this one. You see, it's comparing the key it's comparing the key. This key is compared to the query, and then this key also compared to this query, and this key also compared to this query. So it does the attention 3 times for this step only.
Okay, so for each specified query, the key is the same, right? Or they are different?
Not same. It's different. The key is for this input is for X1. This one, X1 input, it gives the key 1. And this X2, it has the key 2 and key 3.
Then how can we make decision about choosing key 1, key 2, key 3? What's the relationship between key 1 and the query, key 2 and the query?
For X3, it is now X3 is here, and and so they just do the dot product to compare, and if the dot product is close, then there is something. But for example, if this one, the key 1 and X3 is very different, I mean, this is the query of X3. But if it's very different, then this is 0. This is 0, and there's nothing here. But if key 2 is close to the query 3, then there is something here, and that there's a value here, because the value goes through the attention. So attention is just the dot product. The dot product is
okay.
Yeah.
For each attention, there's a threshold value.
For each attention, there is the dot product, and the dot product can be either close to 0 or is close to 1.
How can you define the close?
Because now you have the dot product, right? The dot product is from something from 0 to 1, right? In this range, right?
Okay.
But
yes,
but and then there is the softmax function, and this is important. Now the softmax, it kind of push the values either.
That's why I ask you if there's a threshold value to decide the value could be go through or not, based on the threshold value by using that softmax function.
Yeah. So so you can see the dot product is the kind of the threshold, but after softmax, it becomes like a threshold, and so sometimes it goes through, but sometimes it is 0.
Yeah.
So for example, if this is close to 1, the attention is close to 1, then you have this value. This value is V2. It will go through. But if it's close to 0, then there's nothing here, right? So only this.
Yeah, if it's close to 0.6, does it go through or not? That's my question. How can you
Okay,
define the
yeah.
threshold value?
Okay, so you asked 0.6, but because we use the softmax, and softmax has the property of exponentiation, right? It
Yeah.
exponentiates something.
Right. I knew that.
And so this usually it doesn't appear. So it usually is either close to 1 or close to 0.
Oh, okay.
Yeah.
Okay. But
So
still you need to define the threshold value, right? Like 0.9 or 0.1, right?
yeah. So the for example, you really got 0.9,
Yeah.
and this is the value of
Yeah.
V1, and it
Yeah.
is multiplied. It's multiplied, and
Okay.
then all this will go to the sum
Okay.
for this one for x3. Sorry, this is not true. This is for y3. This is the output y3, and you see why the sum is y3. It's because we are doing the query for x3. We do the query for this one, and therefore the 3 is the output for this guy. You see? So when we do y2, the query would be x2. Do you understand?
Okay, I have one question.
Yeah, go ahead.
So the input number 2, right? You have 4 squares. The query you have 3 squares. Does that mean anything?
Sorry, what?
The input,
you're
right? My understanding is this, right? The input number 1 basically means, let's say it's English, right? The output number 1, let's say it's Chinese or something like that.
Right.
So the key value basically is learned, right? Based on basically it's a training data. That's right. The input is student, output is 学生, right?
Yeah.
So they basically we have the training data, right? 1-to-1 mapping, right? Based on this, we learn the key value, right?
Right.
Okay. But the thing here is that the query, right? What's a query? Query is learned, something we learned, or it's
even the query is also learned because they come from the matrix. I have the matrix where this one.
Okay, I see.
Right? This is input whatever xi, and the query is come from this matrix. It's called Q. It's a matrix.
Okay.
Yeah. So it's all looked up from these matrices.
I see. So so the model is actually the diagram you were just showing, right? Any training data will go through the query, and based on the query, after multiplying with the query, then we get the basically we find out the based on the query, we multiply with the key and find the value and sum up this value together. Right?
Yeah. So that's the self-attention, and there is a formula, but it's in another slide. So let me find the formula. Yeah, this formula is so it's the self-attention formula. So it asks the similarity between the key and the memory item. But actually, it's just the query and the key actually. But maybe the notation I messed up. But this is the attention. Okay. Yeah. Oh, sorry. I wrote this wrong. Maybe this should be the query. This should be the query. It's not K. It's Q. And yeah. So Yeah. So anyway, the attention is the softmax of a similarity measure between it should be the query and the key. Yeah, this is wrong. This is the query and the key. And so now you have this. So you more or less you understand this now, right? How they get the output. This is important. Yeah. So yeah. So basically, this is the transformer, and so I argue that it is kind of like a logic rule, and it will get from the input to an output, and doing something similar to symbolic processing. It's some kind of symbolic process, right? All these memory, I mean the attention stuff will give us some symbolic processing power, and that's the essence of the transformer, in my opinion.
Okay.
Yeah, but I think that it's more complicated in more general AI, right? Because you can just imagine, like the example you give, that about talk about human and then Socrates. That's kind of from general to specific, and then you can from kind of like one situation to another situation, from specific to general. That logic can be very complicated. So that's, I think that's more complicated than this transform.
For example, I have some logic examples here, but this is more general. For example, you have the grandfather, and you father. You mean I mean father XY and father YZ, right? And then from this you can imply that the grandfather is X with a Z. And you need to match these variables in a specific way, from X to X, and from Z to Z, and Y to Y. These arrows have to be matched.
Yes,
right?
yeah. This is a kind of simple example, but I think it's kind of like just you say if just you get a document, or then you try to find all these kind of relations, it will be difficult. Actually, you can imagine that like when you talk, of course, we don't want to talk about politics, but just all these events, like that everybody has his story. And then how can you just like all this New York Times, suppose it's liberal, another newspaper is conservative. How can you kind of like try to find a truth from, just of course, tons of logic here. Like who started first, who started second, who gives the orders, then what is right, what is wrong, what the law says, what is, can be a...
Yeah, but you need to imagine that there may be many, maybe millions of these rules. For example, you have the word Obama, and then it can, that there is some rules that maybe says Obama maybe
he's a Democrat, so he's president.
Democrat. So now,
and he's black, don't know, you can't forget it, he's black. So it's all this.
If you have many rules that can, that many things. He is also a black president, right? And also other things. And if you have many rules, and then all these rules also have other implications, right? So for example, if he's Democrat, then he is maybe he supports certain policies, maybe right. So
Yes, yeah.
So sometimes you can imagine that it can understand the meaning of Obama, because there are so many rules. Yeah, so that's the idea of, and it turns out that the transformer or the BERT model actually can answer a lot of common sense questions. So it can actually answer Obama's, some things. If you ask some questions about Barack Obama, sometimes it can get it right. And,
Yeah, but I mean that their logic is kind of also kind of nested, right? Can you imagine that's the logic is nested, so
Yeah.
that can be I don't know how this transformer.
So it's a dot product, right? The attention. But okay. But here, let's say human model, right? Is that something learned, or is that something?
Yeah, it is learned. Yeah, it has to be learned.
Okay, how do you find out the algorithm learned such rule?
I mean, in the language model, for example, in BERT and things like that, you just predict the next token, and you need to know, you need to understand something about humans to predict the next token, right?
Okay.
So it's forced to learn this kind of knowledge, because if you don't know these things, you cannot predict the next token.
Okay,
So
but the human has many things, right? Human is a model, but the human also needs to eat, needs to sleep.
Yeah.
But how can you learn all this stuff? But among all this stuff learned, why?
Well, for example, if we are talking about eating, so the context, there are some words in the before the sentence that relates to eating, and so it will use the rule that's related to eating, but it's not related to model. It is something else, because this is the context of the of the sentence, right?
Okay. Yeah, so I think it's a
something
concept is that maybe we need something that people are talking about a knowledge graph, right? Maybe that has to be applied.
Yeah, so some people already pointed out that the graph neural network, the GNN graph neural network is actually similar. It's some kind of a transformer. They are very similar. GNN and the transformer. It's actually they are all based on some kind of attention mechanism. Yeah. Have you heard about this this point? Yeah.
Yeah.
Yes. Yeah.
So I think we need to learn some fundamental concept like attention. Yeah, basically, yeah, very good introduction. But I got some idea. Yeah, but
this is a diagram, right? Basically, this is I think it's like this, right? Can you? Yeah. So this is the input, right? Input and output are something we know, or we can know beforehand, right? So input one correspond to output number one, right? The learning process basically is trying to we trying to learn the query matrix, the key matrix, and the value matrix, right?
Yeah, exactly.
And basically, but in the process of learning is that we multiply input with the query, and based on the query, we multiply with the key, and we get the value. We sum up the value, and we're trying to minimize we try to fit this output, right?
Yes, so the query multiply with the key, you get the dot product. But this is multiplied to the value.
Okay.
So this is like a gate, and sometimes it will be 0, and this value would be ignored. So only some will pass through. You understand?
Right. But the thing is like how. Okay. Okay.
Yeah,
okay. The output doesn't even have to. We don't really have to define the output, right? As long as the model, right? The query key value, whatever, that it can distinguish all this input, right? As long as
yeah. So as long as the input will give the output, yeah, it can learn anything. But from any mapping from the input to the output using this kind of memory mechanism. So you can actually compare this to the fully connected neural network, fully connect, right?
Okay.
So even this can all be fully connected, nothing like this, right? And so what's the difference? The difference is that it uses the matrix and it has this equivariant structure.
Right.
And it's a restriction of the fully connected. The fully connected is even more powerful, but it has much more weights. So it's slower.
Okay.
But now if we use these matrices, then it's much faster.
Okay. Here, okay. For the input and the output, right? Here we are using numerical values. Let's see, it's a vector, right?
Yeah.
So how we convert the language, the word, the text file, text string to a vector?
Yeah. So this is a 3-dimension 3 vector, right? So these are actually 3 numbers. But in practice, it may be more like 512 dimension, and this is a very long vector, and we can convert this back to the word.
Okay, so this input and output vector doesn't really matter. We can just assign. We can just run assign, make up some rules, just assign
Yeah.
Right.
And
have
also
to learn, right? So okay.
Yeah, and also you remember, so each one is a word vector. So this is quite long, actually.
Right.
It's a word vector, and then this is concatenated with all these, and if it's fully connected, fully connected, then this would be a very wide neural network. There would be a lot of ways in the fully connected neural network, and you can see that this method actually is much more efficient.
Okay.
Because you only learn the the QKV matrices. I mean, in another slide. I mean, this one. You only learn this one. You only learn these matrices, and then you can find, and then this replaces the fully connected matrix, the fully connect network, right? This replace. I mean, these 3 matrices, and that therefore is very efficient for self-attention.
Okay.
Yeah, a quick question for this here. So here we assume that this matrices can be viewed as storing logic rules. So meaning we can extract the logic rules from the matrix. So my question is, in the BERT, usually we repeat the self-attention layer for 12 times or 24 times. So how to combine this all the matrix and generate the unique logic rules. Because like 12 layer make it 20.
That's a good question. So for example, we have some logic facts here. And so one step, it will give me some other outputs, and then you have another layer, and then some more outputs.
Right.
So, and so on. So that means that when you stack up the transformers, multiple layers of transformers, it's actually similar to performing multiple steps of logic deduction.
Oh, I see. So eventually you will get just one logic rule set rather than 12.
Yeah. So
yeah, it might be a chain rule. So from the beginning to last to the end. I see.
Yeah, and also in each layer, you actually have a different kind of memory. So it's actually a different set of logic rules that we will be using. And this is a good point, because basically, I mean, in theory, we only need one step to from the premise to the conclusion, right? I mean, this is a premise, this is a conclusion. We only need one step. But in the transformer, we actually we split into many stages of logic deduction. So it's also maybe more efficient because we can separate into many different steps. Yeah. Okay.
I see.
Yeah.
Something about maybe not sure whether this is interpretable, and from the premise as a big picture premise to conduction is a high level. With if we dive into deep dive into details, it might be 12 steps or 24 steps. So how to interpret these 12 steps?
That's also a good question. And they study the transformer, and they found out that that there's this paper here. This paper. Can you see this? A mathematical framework for transformer circuits, in which they study the what's happening inside the transformer. So it's a complicated paper, but what they found out is so I explain here, perhaps in this diagram. Yeah. So so what they found out is that sometimes they just use this copy mechanism. Copy is very common, in the sense that, for example, this xi is directly copied to the output. So this is actually same as xi. It's copied. Let's just ignore this. So sometimes they have this copy mechanism, and it occurs very often.
I see. So when the copy happen, it is almost like say A is A, entity A is A, alpha is alpha, something like that. Okay.
Yeah, but it changes the position. So sometimes so why is this important? Is because in the logic, not this one. In the logic, no, we often want to do this copying, but for example, this X has to be copied here, right? Y, for example, the Z has to be copied from here to here, right? So that's why the copying is very common in the transformer, and they actually found out that some of the matrices actually is just doing copying. Yeah.
So when the copy happened, we can just safely skip that layer because they're working the same thing.
Something like this. Yeah. And they found out, and this diagram is the reason. They find the eigenvalue of the matrix. I mean, they consolidate everything into one matrix, and then they want to find the eigenvalue.
I see. So basically, with the eigenvalue, we can, when we interpret the model, we don't have to worry about the 12 layers. We can maybe skip some layers when the copy happening, and eventually we can reduce 12 layers to maybe 2 layers, 3 layers using eigenvector. So then we can interpret that in a much simpler symbolic logic.
Yeah. So if we use the eigenvalue to interpret, so when the eigenvalue is close to 1, I mean, this is the real number 1. This whole thing is a complex plane, and these are complex numbers. But if it's close to here, then it's close to 1. 1 means copy. 1 because if you multiply the matrix A x is equal to 1 times x, so it's just copying. This one is the lambda, which is the eigenvalue. If the eigenvalue is close to 1, then it means copy. And what they found out is that this is the random distribution of eigenvalues. But in many transformers, the eigenvalue is close to 1. And this example shows, for example, they have about 10 eigenvalues, but many of them are close to 1. You can see, right? It's close to 1.
Then the close to 1 eigenvalue can be translated into a predicate relation.
One actually means copy. It's copying.
Okay.
It's just doing copying. But this one is not doing copying. This may be something else. But many of them are close to copying. And so this is very interesting that they found out that
what a copying means it's a waste of time, or means it's doing the right thing?
It means the X is copied from one position to another position.
Okay.
We use a copy to compress the matrix, I guess, or distill knowledge.
It means a good or bad. It means good thing or bad thing.
It means it's symbolic.
I see what you're saying. Okay.
Yeah. For example, human X and then mortal X, and we need to copy this guy to here. Yeah. So it's very symbolic. It's just moving things around and then sometimes changing some symbols, and that's why we think that the transformer is very close to logical manipulation.
Can you give us one concrete example?
Yeah. So just like I gave earlier these 2 examples.
So the input is human X, the output is mortal X.
Yeah, but this one is just from my logic-based AI. I'm very familiar with these rules. Yeah. So
in that case, if we
and also in natural language, it's also similar to logic, but we are doing the linguistic transformations. It's also similar to logical transformations.
Yeah, that's amazing, I think. So then we can automatically transfer any natural language sentence into a proposition, because we can extract rules from the transformer and some rules like a predicate, then combine multiple predicate together, we get a proposition.
Yeah.
I see. That's very cool. Yeah, very cool.
Okay. So the training data basically means Tom is human, Jack is human, and the output is Jack is model, Tom is model, something like that.
Yeah, that can really get a linguistic interpretation of the NLP.
Right. Basically, you use linguistic stuff. Basically, convert Jack is human, Tom is human to human Tom, human Jack, something like that, right? So okay.
So
now you bridge the gap between the formal semantics and computational linguistics.
Right.
Yeah. So basically the transformer. So we may have the hypothesis that the transformer is doing a lot of syntactic, transformations. Syntactic. Okay. So syntactic transformations. Yeah. So that's one of the main points of my, the theory.
You also use that as a dependency parser. So input a sentence, output a dependency parser. So word A depends on word B, word B word depends on word B, and it gives the graph. Then you can further translate dependency parser into a semantic tree.
But sometimes it's not even deterministic. It doesn't need to be deterministic, but I'm trying to find the explanation, but is somewhere. Maybe it's not. So I'm trying to find my the output. I mean that's an important point, but I need to find the diagram to explain this. It actually outputs the probability distribution of the words. But I need to find that the diagram.
Understand. So basically, you would generate a distribution. It's non-deterministic. It could be multiple syntactic tree rather than one.
Let me show how this is done. So basically, you output a vector, right? So and then the vector x is multiplied by the matrix, by a matrix multiplied, and it will. Sorry. I don't know how to show that, but it is an important point. So the vector, output vector, is multiplied by a matrix. This is a long, a tall matrix, and then it gives the output. This is a conversion. This is a matrix. So this is the output vector. And this is actually the real output. The real output. And it's the one, and it's the probability distribution over the vocabs. You understand this? For example, this is apple. This is cat, maybe.
So you get a distribution over vocabulary, and then what's the next step? Then you have multiple possible logic, predicate logic.
No, I mean this is for the in the third model or GPT.
Right.
So when you have the output vector, it's usually it's just a condensed vector, but you for the final output you need to multiply by a matrix, and it gives you the probability distribution over all the words. So this is a probability distribution, and sometimes you can, for example, if you predict the next word to be cat, but sometimes it may be also dog is also okay as another output, but the probability may be slightly less. So So sometimes even if the cat prediction is wrong, but the dog prediction may be correct, and it's a probabilistic output. Yeah. So it's not deterministic. That's what I'm saying.
I see.
Doesn't need to be deterministic. Yeah. This is an important point.
Yeah.
So yeah.
So I'm thinking about even you get distribution is non-deterministic. So one sentence you may get multiple descendant tree, or but it's still we can maybe use some mechanism to calculate generate one tree with the maximum probability, and then in that case we can use BERT as a parser. Yeah, I'm just thinking aloud. Okay, anyway.
But do we agree on the meaning of the deterministic? Do you mean the probability, the distribution, like probability, whatever, will change every time you multiply the matrix? I don't understand, because as long as the probability doesn't change, it's still deterministic, right?
Yeah, the probability doesn't change, but I mean, when you learn the matrices, the probability will change. But but I mean, assume that you have finished learning, then the output is the probability distribution, and it's fixed. The distribution is fixed.
Right.
But you can still, but the output itself you can see this as a stochastic. Yeah,
okay.
Because it outputs the probability distribution. And in some areas, it is very important to have probabilistic output instead of the deterministic output.
I see what you're saying. Okay.
Yeah. So yes, it's quite a lot to cover for today, but yeah, more or less, I explain why I want to use the transformer for logic, and also use reinforcement learning to train this. Yeah. So
okay. Do you have any demo like you can run? I can show. Like...
Yeah. I'm trying to work on a demo now. So I want to use the transformer and reinforcement learning to play tic-tac-toe. Yeah. So it's a very simple example, but it uses logic.
Okay,
I mean,
it will learn the rule and play against basically trying to look at the training data,
so,
right? The stats.
So I want to see if the transformer can play tic-tac-toe logically. And
but logically means it can learn the rule instead of playing like a suicide or anything, right? So
yeah, because in traditional, I mean, reinforcement learning, we just convert this the chess, I mean the bot into a single vector. So this would be a single vector. But this is traditional reinforcement learning. But
right.
in my example, I mean, in my demo, this would be converted to, I mean, for example, the game would be converted to some propositions, logic propositions.
Basically,
and then
stepwise, right?
Do we already have an end-to-end demo from the sentence to
no,
propositions?
No, but I'm still writing. Yeah. But
okay.
And also I tried the tic-tac-toe game for a long time, and I used logic-based neural networks to try to solve it, and it's actually quite difficult. Yeah, it's even more difficult than if we just use reinforcement learning and the bot vector, you know.
Just
so
that end-to-end demo, if it's available, that would be a breakthrough of a formal semantics in the linguistics. Because the formal semantics, those researcher has been searching for such a tool can generate a proposition automatically for many years, for decades. But so far, I don't think there's a good solution for that. If we can build something like that, that would be a great achievement.
Yeah, I guess it is, but many people already see that the transformer may be capable of learning logic rules. So yeah, this is my a long-term research goal.
Okay. So I have a question about AlphaGo, right? So can AlphaGo like playing Go, right? The game. So so is that AlphaGo follows the hard-coded rule that you cannot play. You have to drop like the same color, right? You have to drop on like you cannot drop on certain box, right? That's is that a kind of rule that we hard coding in AlphaGo, but in this case we don't really have to hard code the rule.
Actually, AlphaGo is based on the work of the board vector. And
but I mean, my question is, yeah, but that's just in order to win, right? But in order to actually know how to play the game, right? That when people programming AlphaGo, do they put
No, AlphaGo is not based on the hard-coded rule. That's based on reinforcement.
It's based on
reinforcement learning. Yeah, so
I
they
mean,
have
do we yes, but because every game has a rule, right? Do we? But is that
that's a basic rule. That's basic rule. But how to play?
Yes, that's
how
what I'm
to
saying.
play
I'm talking about basic rule here because the basic rule is important, right? That's the logic, right? That's the basically. If do we have the AlphaGo learn the basic rule, or we basically hard
no. The rule you are talking about is different from the rule AlphaGo is using. Yeah, so totally different. That's basic rule is just
game rule. I'm talking about the game rule, not rule to win, right? So the rule to win is like it's more like a strategy, right? That's so
that's hard point. That's hard point. Yeah. So the rule how to play Go is very simple, right?
It's very simple, but if we don't,
but it's actually hard coded in AlphaGo.
Yes, that's my question. Is that being hard coded into AlphaGo?
Yeah. So I also studied something about AlphaGo, but I forgot many points about it. But it is based on board vector, and well, nobody has tried. I mean, as far as I know, they have not tried using the transformer to play Go.
Right, but in your case, right, in your tic-tac, in your case, do you learn the rule to play the game, or do you hard code the rule in the game?
Actually, some of the rule has to be learned. For example, you see, sorry, this, yeah. So if this is already that there's someone play this, and if you try to play other one here,
right,
then you will be punished. I mean, the computer will be punished.
So you learn the rule here. So
yeah, you cannot play something already occupied, and this will be a reward, negative reward for playing this. Yeah. So in this sense, it has to learn quite a lot of things. Yeah. And yeah, we can also search Google to see if they use transformer to play game of Go. Let's see let's see if there's any result. Yeah, they use transformer to play. Can you see this? They Go transformer. Right.
What's the performance? compared
I
to
don't know, but
AlphaGo?
I have not learned, but yeah, we can see right now. Let's see. Mm, I don't know how good they play, but yeah, as we can expect, they already tried this with Transformer. Can you see the words? Yeah. So yeah, we are seeing the transformer being applied to many areas, such as they also use a visual transformer for object recognition in computer vision, and so it is pretty universal. I mean, some people say that the transformer is a universal, like a computing element. Computation engine, yeah. So this paper, it says that the transformer is a universal computation engine. Yeah. Are we running out of time, or is it?
Yeah, time is.
Yeah, I'm okay. We can chat a bit longer, but I'm free. But
I have a question.
Yeah.
I have one question. So at the very beginning, you said that you are independent researcher, right? So what kind of you work for yourself, or which company or which university?
Where do you get the funding?
No,
no,
that's he has been working on this topic for many years, so that's why I'm wondering how do you make a living?
Yeah, where do you get the funding, right? So
yeah, actually, I try to start some company, but they don't make any money. So for a long time, I don't have any income. And,
oh, really? But how can you?
He has a rich family, right?
But how do you make a living?
Yeah, it is actually from my family, but I'm not really rich.
The money has interest, right? So it's
no, I'm not really rich, but I mean, my family allows me to do this, but and I live on very small expenses for a long time. That's how
that's great. That's amazing. Yeah.
So, yeah, maybe I'm quite fortunate to have so much time to spend on this, but I really need to make money. I'm not okay for a long time, so I need to start making a living.
Your presentation is very great. Yeah, very great. But I think maybe you can make a serious topic. Yeah, dividing this big presentation into several small topics.
Many topics we can.
Yeah, we can follow smaller one each time.
Because I've been working on this for a long time, and I know this very well.
Right.
So I did not prepare for this presentation.
No, that's fine. That's fine. Today it's a general, brief introduction. We learned a lot. Yeah, we learned a lot.
It's just a spontaneous talk.
Yeah.
Not that way. Actually, you think he prepared for his.
I learned the word, from recent,
Okay. So I'm glad that I at least I explained, for example, how the transformer works, and That's good.
But I have actually some fundamental questions, especially how AGI is different from traditional non-AGI, say, non-AGI.
Actually, I mean, if you have seen BERT, and you know that the Google also have a new model called Gotto or something, right? Have you heard that?
Right.
Yeah. So they are actually getting more closer and closer to AGI, and the nowadays the mainstream research is actually almost no difference from AGI, but they maybe they sometimes they don't call it AGI, but actually is AGI. And when you remember Ben Gersel, the guy I introduced in the beginning,
Right.
he was one of the pioneer. I mean, he is one of the pioneers in AGI research, but and he used the logic-based AI approach. But nowadays, the mainstream actually has kind of surpassed all that research, the early research. So the mainstream now is all based on transformers, and that there may be some more new variations. And also, you know, Yan LeCun, I mean the famous researcher. You know this, right?
Yeah, we know.
It's in Canada, right? In
yeah,
okay.
and also Bangio, also in Canada. And these people, they are mainstream deep learning experts, right? But they also start to research in, basically they are researching in AGI now. But yeah, and they also yeah. So, but before we think of these people as deep learning people, right? But now they actually say explicitly that they are doing well, they research into AGI now. Yeah.
Okay, so like a tool, like a non-technical people, basically AGI means the program can understand people, right? Can take orders from people.
Yeah. For example, maybe pass the Turing test or something like that.
Right.
But it is general problem solving.
Right.
And one feature is that it can do multiple steps of logic inference. And this aspect is now at the frontier of research, because sometimes the BERT or GPT, it can answer some logic questions, right? You know, it can, but also it makes some very stupid mistakes sometimes.
Right.
So now the frontier is about how to make multiple steps of logic correctly. And I think the reinforcement learning is a very important step. So we need to put the transformer in the reinforcement learning, because reinforcement learning uses the reward to learn. So we can do many steps and the reward would still be positive. And this is very important. I think this is one of the key steps towards having AGI. Now is close to AGI, but if we can put it in the reinforcement learning framework, then it will be even closer to AGI.
Okay.
Yeah, I actually believe that one of the quick practical application of this research is really in semantics, in formal semantics linguistic study. And there's many linguists, they're searching for this tool for long, as I mentioned before. Maybe you can just talk to them. They will be very interested in this tool, how to convert a sentence into a preposition automatically. This will be super useful to them.
Yeah, so if we can do this, it has relation to knowledge graph and other, you know, the symbolic data. Yeah, so that I think there's a lot of research.
It doesn't even have to be a graph, not a graph that fancy. Just generate a proposition logic. That's enough for those linguists. I think some researcher, they will be willing to buy this tool, because nowadays in the linguistic department, when the professor teach some class, formal semantics or syntax, they usually generate a sample sentence, from using a very simple sentence and draw a constituent tree or semantic tree. They never try from the massive data, natural language data, to generate many trees like this automatically. So they do want a tool if it's available.
Yeah, it is part of the AGI. I mean, the logic-based AI. I mean, I've studied this for a long time. So yeah, this is one of the applications. I mean, but it's not easy because I mean, what we do now, we are only guessing that the transformer has the logic structure, but we cannot actually output the exact logic formulas. It's still something, it is hidden inside the transformer.
I see.
Yeah, so and also maybe we don't even need to output the explicit logic form, but we just try to use the transformer to solve the question answering or things like that.
I see.
Yeah.
Understand. So essentially, you can already explicitly generate a proposition, but you have no idea what exactly the predicate is, because it's kind of hidden, and we cannot using the natural language to describe what is the predicate.
So so we guess that it has some logic structure, but if we actually print out that structure, it may be very complicated, and then the humans may not be readable. But we are guessing that it is logic.
I see. We know we can generate a predicate A, predicate B, but what does a predicate A mean? Predicate B?
It's just okay.
Yeah, but still, it's very promising. Yeah, that's very good.
Yeah. So actually, I want to explain my theory to people, and then maybe someone will join the DAO project, because it is open source, and we try to build some models to closer to AGI. And so my purpose is to want to recruit more participants.
Good idea. Yeah.
Okay.
Well, maybe next time we can you can have a dedicated session talk about this project. Right? So.
Okay. Yeah, and I also will try to write some models to confirm the theory. Yeah.
Right now, are you trying to get some funding for your project?
Yeah. So
that's what the DAO project is about, right? The DAO.
Yeah. So I try to use the DAO to raise funding, and hopefully it will start making some money for myself and also for the project. Yeah.
Yeah, I think some universities and some institutes can support, can provide some funding.
Yeah, I have a difficulty to find a professor willing to take me as a researcher. So yeah, so I mean, I talk to many people, but I mean, the sometimes the university funding is not enough, and then they also, there's a lot of competition from other research students.
Yeah.
Right. So I cannot get in. It's not easy for me to get into a university, and also all the all the companies, I mean the biggest companies like Google and OpenAI, they are from American companies. So there is no global, for-profit companies doing, hiring people to do research in AGI. So currently,
Okay.
Currently there aren't other companies doing this except the American, basically in England and America. So what I'm trying to do is to provide a global project so people can join to make some contributions towards AGI. Because right now, right now you don't have that choice except to join either, for example, Google or DeepMind. DeepMind is in UK, right? And also OpenAI is owned by Elon Musk. But these are the very few companies that are close to AGI research. But I want to provide an open source but it's also for profit, because we open the result as a service on a platform, and we try to make money from that platform. For example, by providing machine translation for free, but we use the profit. We use the platform to like earn some advertising, or for the web, from try to make some profit from the web traffic. Yeah.
Okay.
So
maybe next time you can give us a talk about the DAO project, right? Basically, I think many people are very interested in what's DAO, right? First place, what DAO can do, right? How you basically build the DAO, right? So
yeah. So I'm still starting, and we will look at some platforms to start the DAO.
Right.
And yeah.
Just give us some introduction about the DAO, right? If people
I
join,
I have some friends, and they are also interested in that. They are from India,
right?
And they also helping me to start the project.
Right.
So yeah.
Maybe you can invite him together or her together, basically. Right. So.
Okay.
So we can also post a video on YouTube. So I think right, some people will.
Yeah.
Many people. Yeah. So people can notice if they are interested, they will contact you.
Yeah.
Right.
Yeah. Okay. Yeah. That's good.
Okay.
Yeah.
I'm just curious, which university have you talked to before?
No, I study in New York, but which universities?
Yeah, maybe which university have you talked to them for the collaboration to market your research?
It's mostly people in the professors in Hong Kong. I've tried them all, but they are not interested.
Which department? The computer science or linguistics?
Yeah, computer science. Yeah, mostly.
Science.
Machine learning.
Have you talked to the linguistics people, linguistic researchers? I guess that might be interesting.
Yeah, but I'm from Hong Kong, and I have. Actually, I almost know all the professors in Hong Kong universities.
I see.
They are not too interested. And yeah, it is difficult to find. But that was that was some years ago. And now the research is very different. And
I see.
Yeah.
So I know some people in the City University of Hong Kong and the Chinese University of Hong Kong Linguistics Department. they might be interested in the formal semantics and how to generate a proposition. That might be very interested. Also, Polytech. Some people, researchers in department of linguistics, they might be very interested. Just my recommendation, just my 2 cents.
Thank you. And we can maybe talk about that more online. And what I want to say. I mean, AGI is becoming more mainstream research, and but because of the COVID, I have not gone out to places for a long time, for a few years, and in during these couple years of the COVID, things have changed very much in the AGI, because just a few years ago, if you talk about AGI, it still seems quite far away. But now, in particular, in these few years, is like people are not questioning it so much. Many people believe we are close to AGI now. Yeah. So yeah, I want to talk to more the researchers in university, because I have not talked to them for a long time, and there may be some new professors whom I have not met, even in Hong Kong or even internationally. And also, if successful, I may also invite people such as Yan Likun to the DAO project, just as an advisor or some, yeah, it is possible.
Yeah, if you can invite him together, give us a talk, I think that'd be fantastic.
Yeah, and also I'm a close friend with Ben Gersel, and he also is one of the leading, figures in AGI research.
Okay.
So yeah.
Yeah, if you can invite those, big names, right, together, I think many people will definitely will be interested in this, right? So.
Well, Ben Gersel is not very. I already know he has some difference with me in terms of AGI theory, so he's unlikely to exactly join my project. But yeah, we share a lot of ideas with each other, and
right. If you are close friends, people.
Yeah.
You are right. So you can.
Yeah, it's sort of yeah. I need to organize more better. I mean, to find some people who actually would join the DAO and make contributions.
Right.
So because I've been in this field for a long time, I know a lot of people interested in this field, but they are not at the stage of actually doing some contributions. And
but they can help you to do the marketing or to do.
They can also spread the word that I'm doing this thing, and let more people know this.
Yeah.
So it's been a long time. Yeah.
That's cool. All right.
Okay.
Anybody has any? Patrick, you haven't talked yet. You want to say something? Hello, Patrick. Stop the recording, probably people will talk. I cannot stop the recording.